All right, so here we are. My talk is called Some Aspects of Semi-Transitively Orientable Graphs. And I would like to give you 10 quick facts about these graphs, so you've got some first impression about these graphs. Basically, all graphs considered by us are simple. No loops, no multiple edges. Next statement is that semi-transitive graphs are exactly the same as so-called word representable graphs. And actually, depending on the audience, sometimes I prefer to use word representable graphs terminology, sometimes semi-transitive orientable graphs. The point is that it does not matter. Okay, so whenever I'm talking about one type of graphs, I mean the other type of graphs, and so on. And this will be due to a theorem, classification theorem, which I'm going to mention to you a bit later on. And in fact, I'm admitting everybody. Okay, so I'm getting admission requests, so I'm admitting everybody. And so, by the way, I should tell you that if you have a question, if something is not clear, please don't hesitate to interrupt me at any time. You could either unmute yourself and use your microphone, or you can ask me in the chat. I'm trying to keep an eye on the chat as well while I'm speaking. So please don't hesitate to interrupt me at any time. This would be much easier rather than going backwards later on. So I will give you definitions of everything, actually, of word representable graphs, semi-transitive orientable graphs, and I'll tell you how they are connected. Now, this representation business is actually some small part of a much larger theory of representing graphs using patterns in words. And I'm not going to say much about this in my current talk. This is subject of a different talk. So by the way, I should tell you that to make a comprehensive introduction to the theory of word representable graphs, I would probably need 10 lectures, okay? Not just a single lecture right now. However, I'll select a particular material so that you'll get the chance to jump into the area from the very beginning, okay? And actually even do some research in the area right away. The class of semi-transitive graphs is hereditary. And what does it mean? That means that if you have a graph, if it is representable, word representable, you can remove one vertex from this graph, and what is obtained is still word representable. That's what it means to be hereditary. And I'm sure that many graph theorists like the property of being hereditary. So this is a nice property of my graphs. Okay, I keep admitting whomever I see, okay? Now, the theory of word representable graphs or
I'm sorry, Prof. Sorry, Prof. Sergey. Please just focus on your presentation. I'll be doing the admitting so that you interrupt your presentation.
Oh, somebody is unmuted.
Yes, I said just focus on your presentation. Don't worry about admitting people.
Admitting. You can admit actually.
Yes, yes, just focus.
Okay, excellent, excellent. Thank you. That's a good idea. Okay, I'm not going to click the admit button and let you do it. All right, so the theory was introduced in 2004 based on work in algebra, actually. And this was my joint work with an algebraist from University of Louisville. His name is Stephen Seif. Okay, and based on this work, the idea popped up of a word representation of graphs, and any further developments were given then. So why should you care about these graphs? Because they are proper generalization of much studied and well-known classes of graphs, such as pre-colorable graphs, circle graphs, subcubic graphs, comparability graphs. And I'm not going to define them for you now. This is not the point. This is just 10 quick facts. Not all graphs are semi-transitive. Some of them are not semi-transitive, and the smallest example by the number of vertices of non-semi-transitive graph is the wheel graph W5. Okay, so graph drawn over here. So you can actually represent everything that's smaller than this graph, but not everything that is larger than this graph. Now, for those of you who like complexity theory, okay, then you should know that recognizing semi-transitivity is an NP-complete problem. And this makes this theory even more interesting. Okay, we want to study the properties of these graphs because they are not hard, not so easy to recognize. Now, enumeration of these graphs is known up to 11 vertices. Okay, and a group of computer scientists from the University of St. Andrews, which is not very far away from where I'm speaking just now, they run computations, and it took from them 3 years to figure out how many semi-transitive graphs do we have up to 11 vertices, which I find to be a very impressive result, enumerative result. And there are about more than 45 papers on the area. There is a Springer book co-authored by myself, and there are 2 PhD theses already written on the subject. And there are a couple of master physicists and some other work done. So this is a very quick introduction for you, what we're going to talk about. So this is the area of representable graphs or semi-transitive graphs. And if you would like very quickly to learn about the area and open problems and things like that, so I would recommend you to go to Wikipedia, okay? And there is a Wikipedia page dedicated to these graphs. The page is not very up to date, so much has been done since the page was created, but nevertheless, this is a very good overview, which you can spend, I don't know, half an hour at most, and see what this area is about. And another, a little bit more comprehensive in a sense, on the other hand, containing fewer references, would be a comprehensive introduction to the theory of representable graphs. So this article also can be found online. And this is a very easy reading. In fact, when I submitted this article, it was an invited article. When I submitted it to the venue, the editor managed to read it through a single evening, okay? So he told me that he was so excited about this paper that he read it from the beginning to the very end within one evening and producing some sensible comments as well. So my point is that this is a couple of days reading, say, and then you know exactly what the area is about. And the final option is so-called Words and Graphs. This book written by myself in collaboration with Vadim Lozin from the University of Warwick. And basically, there are a few chapters dedicated to the subject in a very, very thorough manner. You have even some problems here and solutions to the problems. So this is also a good source to learn about the area. And if you will send me a direct request about getting a copy of this book, I'll be happy to share it with you. All right? So you don't have to buy it. Okay, now about this particular talk. The area, as I hope you've got some sense, is quite wide, right? And it would not be possible for me to talk about all developments in the area. However, I selected 3 particular directions in the area, and I would like to introduce you from the very beginning, okay, through known results to actually open results in these particular directions, so that at the end of this talk you could sit down basically and you can do your own research in this direction. And actually we also have these tutorials or demonstration session, or how you call it, problem solving session, if you like. So if you would attend this particular session, then I will try to share with you methods to tackle problems, more methods to tackle problems in the area. And we will even see how software works, how it can help us. I will demonstrate this for you. So please stay for an extra hour after my talk, and you will learn many interesting things. However, okay, so basically these are all references relevant to particular research directions. And I'm not gonna talk very, I'm not gonna cover all the details here, okay? So some of the things I'm gonna jump through, all right? And this is not only because I came late, which is, again, apologies for that, but because the slides contain a little bit more information than I would be able to cover in reasonable time, all right? But in your own time, you could go through the slides, which are available with the organizers, and I'm sure they could share them with you. And you could actually read those things which I'm gonna skip. There will be not many of those, but some of them, right? For the sake of brevity. So I'm trying to see. Oh, okay, thank you very much. So I've got a comment. Of course. So I've got a comment from the person who actually wrote the foreword for this book, which I was talking about. And this is very nice surprise to see you here, Martin. Thank you for coming. All right. Okay, so now one more slide to spend on motivation. So if you are still not convinced that this is an interesting area, basically it came from algebra, study of Perkins semigroup. On the other hand, it's interesting from the graph theoretical point of view, and that's why I'm speaking here in the first place, of course, right? Because this is generalization of several classes of graphs studied so far. Now, it relies on various property of words, and actually the original definition comes from words. And that's why it's interesting from so-called combinatorics on words. And this area is about 100 years old, a little bit more than 100 years. It's now 116 years old, to be more precise, okay? Now, if you are interested in algorithms, then you will see many algorithmic questions in the area. So it's interesting from computer science point of view or theoretical computer science point of view. And then you can actually reduce solving some scheduling problems to this area, so that it's interesting from operations research point of view as well. And it just has beautiful mathematics and some nice arguments, nice constructions and things like that. So it's interesting from mathematical point of view in general. Now, we jumped finally to the very first definition. And I will be very slow at the beginning because I want all of you to understand every single word I'm saying, okay? Once you have the definitions and everything in here, the rest could be skipped. Some places could be skipped and you can read them later on. So basically we have a graph, which is a simple graph again. And we say that this graph is word representable if you can find the word W such that two letters in W alternate. Alternate means that if you ignore everything else, then two letters would come in order. Okay, so you will see examples of this just later on. If and only if these two letters, there is an H between these two letters. Okay, and we have an extra restriction that every letter must be contained at least once in our word. So for some of you, that might be a slightly confusing definition, but let us take an example and I'm sure it will be clear for you. So you give me your favorite graph. For example, your favorite graph looks like this. First of all, notice that this is unlabeled graph. There is no labels. But still, we can talk about representing this graph by a word. And later on, of course, we'll be talking about finding semi-transitive orientation, which comes later on. So if you are talking about orientations, of course, you don't need any labels at all. But I'm talking about representing by word. So I do need labels in this graph. The question is, how do I label this graph? And the answer is, it doesn't matter. So in this particular context, in this particular theory, it doesn't matter how you label your graph, all labelings are equivalent. However, if you look at the wider context of representing graphs using patterns, then labeling might be crucial. For some labeling, you may succeed, for others, you may not succeed. So I decided to label my graph in this particular way, 1, 2, 3, 4. And now I claim that this word represents my graph. So I can encode my graph by this particular word. And the question is why? Well, so according to definition, so for example, if I have an edge between 2 and 3, then letters 2 and 3 must come in order in my word. What does it mean? That means that if I ignore everything except for 2 and 3, and if I read from left to right, so then first letter I meet is 2, as you can see. And next letter I meet is 3. And then I meet 2 again. And then I meet 3 again. So my letters come in order. And I am calling this alternation of letters. That's why I have an H in here. And for example, what about letters 3 and 4? So they're connected, so they should alternate. They must alternate in my word. So first I see letter 3. I ignore all other letters. And then I see 4, and then I see 3 again. Okay, so I have very nice alternating properties. And you should notice, this is a typical question I am receiving, what happens if you have a single occurrence of a letter. So for example, you have a single 5 and you have a single 7. By definition, single occurrences alternate. So I have alternating property. So I have no problems with that. On the other hand, you can see that there is no H between 1 and 4. No H, which means that 1 and 4 must not alternate in my word. Okay, so let's see. First, I see 1. If I go to the left, or to the right, sorry, I expect to see a 4. But I don't see any 4. I see 1 again. So I broke the alternating property. And this is sufficient to break the alternating property just once in order to claim that there is no alternation. So I don't care if 1 and 4 will be alternating afterwards. I don't care about this. I broke the rule once, that's it. There is no H whatsoever. Okay, and you can actually check each pair of vertices here, and you can see that all of them have the right alternating properties. Alternate H, no alternation, no H. And I should stop just here, and I should ask you, do you have any questions about the definition of a word representable graph? Okay, so it seems to be clear. So given graph, label it, or maybe you'll be given a labeled graph already. And then your job is to try to find a word that represents your graph. Basically, that's it. Okay, if you succeeded in this, that's fine. The given graph is representable, word representable. But if you didn't succeed in this, and if you can prove that this is not possible, then your graph is not word representable. Okay, there are few properties of words representing the graphs. For example, if you can represent it in one way, then there are infinitely many ways to do it. For example, okay, and I can create as long representations as you like. This is one particular property. Okay, but there are some other properties which I'm not gonna talk about. All right, so now I'm gonna review some notions that might be well familiar for you, but this is transitive orientations, what it is. Orientation of a graph. So you see, I started with non-oriented graphs, and now I jump and try to define something in oriented graphs case. And of course, we will have some other talks about oriented graphs, and this will be useful for you to recall. So basically, an orientation is transitive if whenever I have an H from U to V, and I have an H from V to Z, and U, V, Z are vertices in the graph, then I must have an H between U and Z. So this is how we know the transitivity in mathematics, basically, right? And comparability graph, on the other hand, this is non-oriented graph that admits a transitive orientation. So you give me a graph of your choice. If I'll manage to produce a transitive orientation on this graph, then I claim that the original graph was comparability graph. Otherwise, the original graph is not comparability graph. And the smallest example of non-comparability graph is given this 5 cycle. Okay, so normally I would demonstrate why this is not a comparability graph, but now because we started late, let me just move forward to some other things. All right, so there is a theorem, which is a very, very nice theorem, which is saying that if the given graph is word representable, okay, so if you can represent it as by a word, then the neighborhood of each vertex in this graph is a comparability graph. So neighborhood, basically, you collect all vertices connected to the given vertex, right? And you keep all the edges between those vertices, and that's how you talk about neighborhood of a vertex in the graph. And if the graph is globally nice, meaning that you can represent it by a word, then it must be locally nice, meaning that looking at each neighborhood, you will meet a comparability graph, which is nice, right? And on the other hand, the question is, what about the other way around? If you give me a graph, and if this graph is locally nice, neighborhood of which vertex is a comparability graph, can we conclude that the big graph is also nice? I can represent it by a word. And the answer is no, it does not work the other way around. And we have 2 examples here, smallest examples of the situation. So basically, if you would be looking for neighborhoods of each vertex in this graph, then you'll see that this is a comparability graph. You can orient it transitively. However, all the graphs themselves cannot be represented by words, which was proven. And I have something in the chat. My view is still stuck on slide 3. We'll try rejoining. Oh, okay. This is Nicholas. Nicholas, you're on the call already. Back. This is everybody else can see the slides well. Oh, it's okay now. Okay, yes. Thanks, Nicholas. Yeah, thanks for coming, by the way, Nicholas. Now, Nicholas is a student of Vadim Lozin, co-author of my book. Right, now, former student, I should say. Nicholas is not a student anymore, of course. Now we come to the definition, most complicated definition, technically complicated in the entire talk. So I want to make sure that you understand it, okay? And even if you don't understand it, then please wait for an example. I will give you an example. And after looking at this example, hopefully everything will be crystal clear for you, okay? So basically, there are various types of orientations. And one of the best types, probably you know, most popular type is acyclic orientations, when you don't have any directed cycles. So my orientation of a graph is called semi-transitive if it is acyclic, there are no directed cycles, and there is one more extra condition, okay, which is a bit difficult to explain, but I will explain it to you. All right, so what is the second condition? The second condition is, if in the oriented graph, you will be looking at a directed path of length at least, okay, at least 2, or I should say probably at least 1. Okay, the reality is we should be looking at length at least 3, because length 2 will never cause us any problems, okay? So think about T actually here being 4, I guess. So I want 3 directed edges, all right? But the definition is consistent for smaller cases as well. So basically, I have orientation. I am looking at directed paths of length at least 3 edges. And then I could have 2 scenarios. The first scenario is there is no edge from the first node and the last node. So this is an easy scenario. Okay, so this is a directed path, and then there is nothing from the beginning to the end. In this case, I can ignore this directed path, it does not cause me any problems. And I am looking at another directed path, okay? And my job is to go through all possible directed paths without repeated vertices, of course. The second scenario is that actually there is an edge from the first vertex to the last vertex, okay? There is an edge directed. And then I require from my orientation all other edges induced by these vertices actually be present, okay? And of course, they will be oriented from smaller index to larger index here because I don't have any directed cycles. Okay, so once again, either nothing from the beginning to the end, no directed path, or I must have a transitive graph induced by these vertices. Okay, so all possible edges are present. And now, if transitivity is broken, my entire graph becomes non-semi-transitively oriented. Okay, so I'm trying to see. So you give me a oriented graph, and I'm trying to figure out if it's semi-transitively oriented or not. First, I check that there are no directed cycles. This is fine. And then I will check for every directed path, I will check this particular property. Okay, locally transitivity sort of. And if locally transitivity is broken, then in such a situation, so I have a path, I have a directed edge from the first vertex to the last vertex, and transitivity is broken, then this edge from the first vertex to the last vertex is called the shortcutting edge. So we have some special term for it, which is convenient to use, basically. Okay, so when you're working with orientations in the graph. And the whole subgraph, which causes me problems, would be called a shortcut. And you might wonder where this word shortcut came from. We just invented this word because of going the long way, you can go a short way from U1 straight to UT. Okay, and that's why we were thinking, okay, we should call this type of graphs a shortcut. And remember, shortcut is not transitive. Something is broken there. At least one H is missing. Okay, I'm actually not taking any questions right now. I think you should see an example first, okay, where I repeat all the definitions. And then if it will be still not clear, then we'll go again for the definitions, right? And semi-transitive orientation can be called by me acyclic orientation and shortcut-free orientation. So remember, shortcuts is something bad for me. I want to avoid them. Shortcut-free acyclic. This is semi-transitive orientation. And what is a semi-transitive graph? A graph admitting a semi-transitive orientation is semi-transitive. Okay, so I start again, no orientations, there are no orientations. And then if you'll manage to find semi-transitive orientation, I'm telling that my original graph is semi-transitive, okay? And actually in some papers on world representable graphs and semi-transitive graphs, the term semi-transitive is also used for semi-transitively oriented graphs, okay? So if your paper is about directed graphs, if you don't have any undirected graphs, then you can call a graph-oriented graph semi-transitive if it's oriented semi-transitively, basically. This is just for brevity. It will never cause you any confusion, I believe. And the main theorem in the area, this is still the main classification theorem, is saying that a graph is world representable if and only if this graph is semi-transitive, okay? And basically, recognizing semi-transitivity is the same as recognizing world representability's NP-complete problem, okay? In the extra hour, which I will have after my lecture, I will give you examples of the situations when it's easier to deal with word representability. So it's much easier to write down a word representing a graph rather than trying to find a semi-transitive orientation. However, in most cases, the other way around is nicer, is easier, meaning that you are trying to find semi-transitive orientation, okay? And if you are graph theorist sitting on this call, then this is a good news for you. If you don't like words, then you can forget about them, okay? So you can focus on semi-transitive orientations only, with the main problem being, given a graph, is it semi-transitively orientable or not? Okay, and then you can forget about words. There are no words here. All right, let's try a demo, okay? And I will try to draw something for you. So basically, what is the main challenge? Because the problem of recognizing is NP complete, recognizing of semi-transitivity, we have kind of a bottleneck in the theory, in a sense, meaning that how do you justify that a given graph is not word representable or not semi-transitively orientable, not semi-transitive, okay? So this is really a problem, because the referees, unfortunately, do not like us referring to software. I'm going to talk about the software available for you to help you with this area. So basically, the referees don't like references saying like software told us that this graph is not representable. That means that it's not representable. So the referees want a proof, okay? And the proof, actually, you don't have lots of alternatives here, because either you find a smart argument, what we've done in several papers, or you have to use so-called branching process. And what I'm going to do here as a demonstration, I'm going to demonstrate for you few steps of the branching process without going the whole way in the branching process. And this process could be, of course, a disaster if your graph is big enough, right? On smaller graphs, it works nicely. However, we developed software in collaboration with Hauran San, and this software tries to find for you proofs of non-representability in the shortest possible form. Okay, and I will give you a demonstration how to use this software, which actually eliminates the necessity of dealing by hand with smaller graphs. Okay, these proofs can be produced by you, by software. You can copy paste this proof to your paper, and you can present it to the referees, basically. And this would be something that could be verified by a human. Okay, it's not like referring to a computer proof, but that would be human verifiable. Anyway, so I'm gonna try to annotate, and let me see. So, for example, okay, so you see a graph here, right? And you may remember, if you have a good memory, in one of my original slides, I told you that this is the smallest non-semi-transitively orientable graph or non-word representable graph. So one way to prove this fact is actually a very, very quick proof using a theorem which I presented for you already, okay? So basically, you can notice that neighborhood of the middle vertex is a non-comparability graph. So this is the cycle C5. And remember, I told you C5 is not transitively orientable, right? And I'm done. I can use the theorem. Oh, I found neighborhood of my graph, which is not transitive or not comparability graph. So I can conclude that the entire graph is not word representable, not semi-transitive. And I will be done. Okay. And actually, this quick test may help you. So you might be dealing with larger graphs in your research, but you might be lucky enough to locate a non-comparability neighborhood if you are lucky. In which case, you don't need to prove that the entire graph is not semi-transitively orientable. All you need to do, you need to prove that this particular neighborhood is non-comparability. And this is a polynomially solvable problem already. Okay, so we do have a quick test, basically. So if you are good at programming, you can write a program and you can find algorithm in the internet of checking comparability of a graph. And then you can scan through all neighborhoods quickly. And you can see if you will be lucky, if you can locate this non-comparability neighborhood. Unfortunately, if the test will be returned that all neighborhoods are comparability graphs, then you're in trouble, essentially, right? Then you need some other arguments. And then you need the branching process as the first and straightforward kind of brute force approach to solve the problem. So I will try to demonstrate you how to prove that this graph is not word representable, not semi-transitive. So you want, basically, what is the idea? I'm gonna orient partially the graph, okay? And I'm gonna use certain property, which I'll describe for you, which helps me not to go through all possible branches, but it helps me to reduce the process, okay? So the first thing, however, I'm gonna say, without loss of generality, I can assume that this edge is oriented upwards. So why I can make such an assumption? Because if my orientation is semi-transitive, then reversing direction of all edges gives me a semi-transitive orientation. Okay, so that means that I can assume without loss of generality that this edge particular is oriented upwards, right? And this will reduce, so if you think about full branching, this will reduce twice the number of things I need to go through. Okay, so this is a very strong reduction from practical point of view. Not strong from theoretical point of view, of course, but from practical, it's a big deal. What I'm gonna do next? Next, as I told you, I'm gonna use the branching process, all right? And the branching process tells me, take some edge here and consider both possible orientations. So in other words, I'm gonna copy the partial orientation I have so far, okay? And so I'm creating copy number 2. So I'm trying to bring you to automatically produce proofs. So they're kind of syntaxes and things. So there we create copies. So this will be called copy number 2, all right? And in the first copy, I could orient this downwards. And in the second copy, I could orient this upwards, okay? So now, if you look, and then I am working with copy number 1. So I try to work as much as possible, but whenever I need to branch, I branch it and I create a new copy, basically. That's my approach. And I'll consider every copy, and if at the end, I will see that I'm getting contradiction always, I can conclude that there is no semi-transitive orientation. That's how I'm going to do it. So if I look at the first copy, the thing that you can notice is that I don't have to branch just now. Why not? Because you can pay attention to this particular triangle here, okay? So what you can notice here, there are 2 edges oriented in one direction. So if I orient this edge from right to left, then I will be in trouble because I will create a cycle. But remember, semi-transitive orientation has no cycles in it, which means that there is no need to branch on this edge. I know for sure that if semi-transitive orientation exists, this particular edge must be oriented from left to right. So I hope it makes sense to you. Good news is that I can actually get more information. I still don't need to branch. And why not? Because let me just zoom in this picture for you, okay? So this partially oriented picture. And what I have here, that picture looks like this, right? So look, if I claim that the orientation of these 2 edges is uniquely determined, okay? So why this is so? Let me tell you why this is so. For this, let me just create one more copy here, okay? And think about this particular edge here. I claim that it must be oriented upwards. This is my claim. Why not downwards? Okay, that's exactly why I created this small picture here. If it would be oriented downwards, okay, then you will have problems with orienting the remaining H in this full cycle. What kind of problems you are having? Well, if you orient it upwards, you create a cycle, right? Oh, actually, you'll be creating a triangle cycle, but it's not important, okay? So you will be creating a cycle. This is not good. However, what's wrong with orienting it downwards? But actually, you are creating a shortcut. Where is my shortcut? Imagine yourself staying here, okay? So this is you staying here. And you can go a long way here. Okay, long way meaning length at least 3. Remember, this is important. You can ignore length 2 paths. So length at least 3. But you can also go a short way. This is my shortcutting H, if you remember the terminology. Shortcutting H. Okay, and it's important that I don't have an H here, which means that I cannot make this graph transitive. So oriented graph is not transitive because I have an H from here to here, from here to here, but I don't have a direct H. Okay, so this is exactly the definition of my shortcut, which is telling me that I could not orient this downwards. I have to orient it upwards. And then similarly, there is no choice. So whenever you oriented 3 edges in the full cycle, the 4th edge will be uniquely determined. You don't have any choice, because if you orient it upwards, you create a shortcut. This is my long way, would be my long way, and that would be my short way. Okay, so you want no shortcuts. That means that you must orient it downwards. So basically, looking at this figure without doing any extra job, you can figure out, okay, this is a directed path of length 2. I need to block this path, and I need to follow the block. That's how we say it, okay? Block it, follow the block. This piece is semi-transitive so far, okay? And it's important that there is a generalization of this result if you have a cycle, long cycle, okay? And if in your long cycles, everything is oriented in the same direction, except for 2 edges, okay? Then the orientation of these 2 edges will be uniquely determined. And of course, I am assuming that this is not complete graph induced, okay? So if it's induced complete graph, then I cannot say anything. But this is not induced complete graph. It's not a clique, okay? This is not a clique because I am missing an edge. So if this is not a clique, and if you spotted many edges oriented in the same direction, then you know exactly that these 2 edges must be oriented in the opposite direction, okay? So basically you orient them oppositely. And this idea was used in the software to produce shortest proofs. And I will say a few words about this later on. Okay, so I hope so far so good for you. And we continue our branching process. And at this particular stage, we have to branch again. So there is no extra information you can extract from this partially oriented picture. So branch again means create copy 3, okay? And then copy the orientations you have so far. Okay, that's exactly what you're gonna do. And then you branch on one of the edges. Okay, actually, it's which edge do I branch on? I would like to maximize usage of this particular theorem, you know, this property, in order to reduce the number of branches. So in particular, I would not be interested in branching this edge, okay? Instead, I would be interested in, for example, branching this edge here, for example, okay? Which will help me to decide everything, as you will see in a minute. So I am branching on this particular edge. So let me orient it downwards here, okay? And I must orient it in the opposite direction. I must orient it upwards here. And this copy I will deal with later on. Instead, I'm focusing on this particular copy. So, and the question is, it's like solving Sudoku, basically. You need to focus in the right place in a big partially oriented graph. And the right place to focus on would be at this full cycle over here, okay? So this is my full cycle. And I already told you, if 3 of the edges in the full cycle are oriented, then you can uniquely orient the final edge. And you can easily see that this edge must be oriented from left to right. Because if I orient it from right to left, then I'm creating a shortcut. My shortcut with me staying here, going a long way, and then going the short way, right? So this orientation is determined, which is nice. Once I determine this orientation, I can focus on this particular full cycle, right? Because I'm in exactly the same situation as I described for you here. Namely, all but 2 edges are oriented in the same direction, which means that 2 remaining edges must be oriented in the opposite direction, okay? So I orient it like this. And then I could look, for example, at this full cycle here. And in order to avoid a shortcut, I must orient my edge in this direction. However, I claim that I created a shortcut. So you see, I was following step by step. I was very careful. I didn't want to introduce any cycles or shortcuts, but I still introduced a shortcut. And if I label the vertices for you, can somebody tell me where the shortcut should start, where the long path should start? At the vertex, which vertex there is a shortcut? And this is like solving a Sudoku, I told you. So you need to find the place to focus correctly. No ideas, no guesses. Okay, so basically the shortcut is created starting from this vertex here. So imagine yourself staying here, okay? And then you go the long way, and then you go the short way. And of course, this is not a click. This is not a complete subgraph, right? So I can cut this edge, this branch. You know, I was going in this way all the way down here, and I got a contradiction. So I can say contradiction, which means that this branch will not give me a semi-transitive orientation, right? So I now have to jump to another copy, partially oriented copy, and I need to do exactly the same thing. So I am gonna do it for copy 3, and then I'll stop the process, and the rest will be done in a similar way. And this is a good exercise. Just one quick comment: the software which is available on my page, which I'll mention about in detail, slightly more detail later on, could help you to find shortcuts. So for example, you created in a larger graph, oriented graph, and you spent a minute or 2 trying to find a shortcut, and you could not see any shortcut. What you could do, you could actually take your oriented graph and you could feed it into the software, and the software will find very quickly a shortcut for you, because this is a polynomially solvable problem, all right? To see if a particular orientation contains cycles or shortcuts, okay? Anyway, so let us jump to copy number 3 here, and you will see that in this particular 4 cycle, everything but 1 edge are oriented. So we must be able to orient the remaining edge, and we do it from right to left, because otherwise you could have a shortcut. You would have a shortcut starting from here, going all the way around, and then shortcutting. Not good at all, okay? And then you can pay attention to this for cycle now, right? Two edges are oriented in the same direction, two other edges must be oriented in the opposite direction. And then you can look, for example, at this for cycle here, and you see that this edge must be oriented in this direction, because otherwise you have a long path and then you have a short path, and this is not good at all, right? And if I label again in the same way, I label again my vertices. Can somebody tell me where the shortcut is started, at which vertex? Because to be honest, I don't see it myself just now. Okay, but it must exist because this graph is not semi-transitive.
Start from 5. Start from node 5.
From 5 and then going
5, 4, 3, 6.
5, 4, 3. Oh, that's right. 3, 6. Correct. Very good. So if you imagine yourself staying here, and if you are going the long way, right, then you have a short way. Okay, and we are in trouble. So this is a contradiction. So meaning that this particular branch will not work. So basically, then you jump to copy 2, and then here you cannot conclude anything. So you would have to create to branch on another edge, and it would be natural to branch on this edge because, okay, so you would create copy number 4, and then because if you go down, right, and you make it up here, now you can apply this theorem again. So basically, the idea of branches is you always try to branch on the edge that would allow you at least one application of this theorem, if possible at all, of course. It's not possible for all graphs, but if it's possible, then you want, you know, some applications like then you have already something, and then you take it from there. Then you see this is another for cycle, so you can just keep going, and then there will be another for cycle, and then you can keep going, and so on and so forth. Okay, I'm not going to finish this one. So this is basically the idea of the branching process, and that's exactly how you present your non-semi-transitivity in papers, scientific papers. So you describe this process, and actually we develop the language, because you're not gonna draw many pictures, and there is a nice language kind of which encodes your proof into lines, and your job is to try to create as short proof as possible, so that nobody got tired from reading a very, very long proof. Okay.